So in the first three examples on for rational functions, first of all, what a rational function is it has a polynomial in the numerator and the denominator. And it looks like f of x equals 1 over x, which is the parent function for inverse variation functions. And all a rational function is a type of inverse variation, where most of the graphs are going to look very similar to this one here. You have asymptotes, which are lines that the graph is going to get closer and closer to, but never actually touches them. So for the parent function 1 over x, it has a vertical asymptote at x equals 0. That's this dotted green line. And when you draw asymptotes on your paper, you have to have dotted lines for them. Okay? And it has a horizontal asymptote at y equals 0. So that's that red dotted line. So the graph of 1 over x gets closer and closer to both of those, but never actually touches them. Okay? So, and it doesn't cross the x-axis either. It stays there. Now, there's two different ways you're going to see rational functions. One of the ways is shown here, where the value of a tells us whether it's stretched out or compressed, and whether it's reflected or not. So when the value of a is positive, it'll look like this in the first and third quadrant. Okay? And if it's negative, then it would be in the second and the fourth quadrants. The value of h is a horizontal translation. So that tells us how much it's moved to the left or how much it's moved to the right. If h is a positive number, like it appears here because it says minus h, then it moves to the right. If it was to say x plus some number here, then it would be moved to the left. The value of k is a vertical translation, which tells us how much is moved up or down. So basically all we're doing is we're taking this parent function here, 1 over x, and we're going to move it up and down or left and right. Maybe stretch it out a little bit. But that's the main thing. Okay? And so you already did some of these, right? So you're all good with these. Okay. At least the people that did them. So they give you, so this right here, this little chart here is also on that half sheet of paper I gave you on Friday. Then it tells us that there's a vertical asymptote. Oops, come back here. Right. Vertical asymptote is the line x equals h. And when we talk about domain, then we would say that x is all real numbers except for that value. Because where we have that vertical asymptote, that's where the denominator is equal to 0. And the function doesn't exist there. So we would just say that x does not equal that value for our domain. The horizontal asymptote is the line y equals k. And notice, they're saying that these are lines. So for the vertical asymptote, it has to be x equals some number. The horizontal asymptote is y equals some number. And then the range for those would be that y is not equal to k. So I'm going to go ahead and do this example here then, just to go through one for you. So it says to identify the asymptotes, the domain and range of this given function. So we need to, first of all, determine the values of h and k. So Amanda, what's the value of h for this function? -3. All right. And the value of k is what, Zach? -2.
How is h -3?
Because if you notice, it's x minus h, and this is a plus sign, so it means it would be the opposite. Okay? And also think of it this way. what would cause the denominator to be equal to 0? Negative 3. Okay? Okay. When we're doing horizontal translations, it's always the opposite. Okay? Because it's like, what would cause that to be equal to 0? Okay? If I put negative 3 in here, the denominator to be equal to 0. Okay? So that, excuse me, so that means that we have a vertical asymptote at x equals negative 3 and a horizontal asymptote at y equals negative 2. Vertical asymptotes are x equals h. Horizontal asymptotes are y equals k. So then our domain then would be that x is not equal to negative 3 because it exists for every value except for that one. And the range is y is not equal to the value of k. So let's look at it graphically. First of all, let's look at the thing about the parent function for a moment. We have the parent function 1 over x. Has a vertical and horizontal asymptotes are on the axis. And the graph looks like this. Okay. There's the graph of our parent function. So the graph, though, of this function we're working with, because it says the vertical asymptote is now x equals negative 3, that means that we have moved this vertical asymptote over to negative 3. The horizontal asymptote is y equals negative 2, which means that we've moved this horizontal asymptote down to negative 2. And then this graph then, oops. The graph then, that means then that this graph is moved to there. So all I've done is taken that parent function and moved it 3 to the left and down 2. Now sometimes we might have a number here instead of 1, and that would mean it would be stretched out a little bit further, okay? But my main thing for you to understand is where are the asymptotes and what does the graph look like in there. So when the functions looks like this, you find h and k. H is what makes the denominator equal to 0. K is what we're adding on to the whole function. Then we just move the parent function 1 over x. Yes, Gage?
How do we find the points?
To make it perfect? No.
Well, we don't have the graph that's problem.
Yeah, you would.
That's it. Example 2.
Doesn't. Eventually you will. You will have some that you'll need to graph. Understand this, Gage, that if I have horizontal and vertical asymptotes, my graph's generally going to look like this. Okay. Right. Yep. And your asymptotes should be in the right spots, and then your graph can be an estimate of that, but your asymptotes have got to be correct. Okay, so that's what I'm really looking for. All right. Yes, those are the dotted lines. Yep. Now we have zeros and vertical asymptotes. If we have a polynomial in the numerator and a polynomial in the denominator. Any place that the numerator is equal to 0 is where we have zeros. That's where the x-axis, we have x-intercepts. And where the denominator is equal to 0, we have vertical asymptotes. And we're not going to do this one. We're going to wait until we go into the next problem to do it. So, right? But where the numerator equals 0 is where we have zeros or x-intercepts. Where the denominator is equal to 0, we have vertical asymptotes. All right. Okay. Horizontal asymptotes. Okay. Now, horizontal asymptotes are basically what happens when the values of x are really large or really small. And the horizontal asymptotes depend upon the degree of the numerator and the denominator. And I'm going to show you how you can specifically do it without necessarily knowing without having to worry about the degree, or you can use that says if the degree of p, which is the numerator in this case, so we're looking right here, if the degree of the numerator is greater than the degree of the denominator, there's no horizontal asymptote. So if they ask you for a horizontal asymptote, you would say none. If the degree of the numerator is less than the degree of the denominator, you do have a horizontal asymptote, and it is specifically the line y equals 0. And I'm going to explain to you how these things work as we go through this. If their degrees are the same, then the horizontal asymptote is going to be y equals, and it's the ratio of the leading coefficients. Whatever leading coefficient is in the numerator over the leading coefficient of the denominator. And like I said, we'll look at all three of those situations here. Okay. All right. So this problem asks us to identify the zeros and asymptotes of each function, then graph. So the first thing we're going to do is we are going to factor anything that can be factored. All right? So number one thing to do is to factor it. So when I factor this, we get x minus 4 times x plus 1 over x. So if you look at that sheet of paper I gave you, that little half sheet has this information on it. Okay. Intercepts or zeros. X-intercept zeros are the zeros of the numerator, but not zeros of the denominator. So we want to find out when is the numerator equal to 0. Well, when it's in factored form, that's easy to see. Okay. What are the zeros here? Okay. So we've got 4 and negative 1 are the zeros, because that's where the numerator is equal to 0. Because if I put 4 in here for x, 4 minus 4 is 0. 0 times any number is 0. And 0 divided by any number is 0. Okay, so those are the zeros, 4 and negative 1. Okay, that's where the numerator is equal to 0. The vertical asymptotes are when the denominator is equal to 0. We talked about excluded values, right? Or where a function is undefined. Well, where a function is undefined is usually where there's a vertical asymptote. So in this case, it's undefined at x equals 0. So that would be my vertical asymptotes. And vertical asymptotes are always x equals. vertical asymptotes, where the denominator is equal to 0, but not the numerator, represented with a dashed vertical lines in the equation x equals. Horizontal asymptotes. Now, horizontal asymptotes depend on the degree of the numerator and the denominator, but they also refer to what we call end behavior. Okay, we've talked about that, haven't we? All right. Now, when we're talking about end behavior, we're talking about very, very large values of x, or very, very small values of x, like million, 2 million, 3 million, negative 1 million. Okay. If I look at this function, if I put really, really large values of x in, okay, so let's say 1,000. Right. If I put 1,000 in here for x, x squared is equal to 1 million, right? Okay. Does this negative 4 affect 1 million very much? No, it doesn't have much effect on it at all, does it? Okay, would you even notice it? No. Okay, if somebody gave you $1 million and then took $4 away, would you really care? No. Okay. Right. So if we put 1,000 in here for x here, so we had 3 times 1,000. So if somebody gave you $1 million and took $3,000 away, would you really care? A little bit, not much, right? Because you still have a heck of a lot of money. But you can still buy 900 and some thousand 2 liters. Okay? So this wouldn't matter much. So when we're looking at horizontal asymptotes, we're going to focus on the term with the largest degree in the numerator and the denominator. So if I only focus on them, because the other ones really don't affect them much, we end up with x squared over x. Well, what does x squared over x reduce to? Or x, right? Right? If I have 2 x's in the numerator and 1 in the denominator, I can cancel one out. Okay? So this is equal to x. Well, what kind of a line is y equals x? It's just a diagonal line, right? It's not horizontal, is it? Okay. So in this case, horizontal asymptotes, there's none. Because the degree of the numerator, which the degree here is 2, the degree of the denominator is 1. So anytime the degree of the numerator larger than the degree of the denominator, we have no vertical or horizontal asymptotes. All right? And there's my proof of why. When we start looking at really, really big numbers, that's what happens. Okay? So let's do the graph then. So first of all, I have zeros at 4 and negative 1. And I have a vertical asymptote at x equals 0. So that means I'm going to draw a vertical line on the y-axis where x equals 0. Okay, it's a vertical dotted line. Right? When you draw the asymptotes, they are dotted lines or dashed lines. Okay. Now, to graph this. Now, reminder, it says for asymptotes, the lines, the graph gets closer and closer to it, but doesn't actually touch it, right? Okay. So, either this graph is going to, because there's no horizontal asymptote, either this graph is going to come from somewhere here and go down this way, or it's going to come from down here and go up that way. It's going to get closer and closer to the y-axis, but not actually touch it. Okay. How do I know which way it goes? Because it's got to go through that 0. How do I know which way it goes? Do we know? Is there a way to figure it out? How could I figure it out? Do what? Nope, there's no k in this case. Nice try. Okay. But either we could graph it on our calculator, or we could use our brain and plug in some points. Okay? Now, let's choose a value left of -1. Okay, -2, that's fine. Okay, so if I put -2 in for x, let's see what happens. So we get -2 squared minus 3 times -2 minus 4, and then we have -2 down here. Okay. So that's positive 4, right? And -3 times -2 is positive 6. So 4 plus 6 is, and 10 minus 4 is 6. 6 divided by -2 is, okay, so at -2, it's -3. Okay. So that means the graph is going to come from down in the bottom left and go up to the asymptote. So this graph is going to work its way from over here and come up and go up there. And we're going to graph this on our calculator in a minute too to verify. Now, here's one of the things that happens with these graphs. When the graph goes along the vertical asymptote, if it goes to positive infinity on one side of the vertical asymptote, it's going to be at negative infinity on the other side. Because what happens is we have a sign change when we cross the asymptote. Okay? So where this side, the left side, goes to positive infinity, the right side is going to come from negative infinity then and go up through our 0. And the graph's going to look like this. Now, one of the things that, and this is really, I find it interesting, you may not care, but in Algebra B today, we did the basic rational functions and asymptotes. So we were graphing the basic ones like the 1 over x minus h plus k. Right? In pre-calculus, they're doing rational functions right now. So if you have a friend, brother, who is in one of the other classes, Algebra B or pre-calculus, then they're doing very similar things, and you could actually work together, help them help you, whatever you needed to do. But it's just kind of interesting how that happens sometimes, that we're doing everything at the same time. So let's look at this graph on our calculator then, so you can see what it looks like. So we put our alpha y equals, so we have our fraction there in the numerator. Put in x squared minus 3x minus 4. And it doesn't matter if you put the factored version or the regular one in there. I always like to go back to the original so that I know I'm putting it in right. Alpha y equals. And you can, you can do it the old way, put stuff in parentheses and use and divide. Right? So now when I graph this, zoom 6 and draw my graph. And hey, that looks a lot like what we did there. Now, I want everybody to do this on your calculator. Okay? Make sure you've done it, because we need to check something out on your calculator. Okay. So you can see that we got the correct graph then. And in general, from what we're doing right now, this is what your graphs are going to look like if you don't have a horizontal asymptote. Okay? One of the things we talked about in pre-calculus today is you can actually figure out what this asymptote is. It's called an oblique asymptote. And sometimes we have some that are called parabolic ones, where they actually, as you get farther and farther away from the x-axis, or from the y-axis, they actually look like a quadratic function. Okay? So, all right, there's one thing. If the degree of the numerator is larger than the degree of the denominator, we don't have a horizontal asymptote. Okay? All right, let's look at another one. Letter B. Our function is x minus 2 over x squared minus 1. And once again, we're going to find the zeros, vertical asymptotes, horizontal asymptotes if there is one, and then graph it. And the first thing you always do is factor. Anything that can be factored, factor it. So when I factor this, I get x minus 2 over x plus 1 times x minus 1, those quantities. So where's it equal 0 at? Okay. Positive 2. Where the numerator equals 0 is where the zeros are. So this has 1 0 at positive 2. Zeros, same as x-intercepts or intercepts, zeros of the numerator. So when is the numerator equal to 0? Vertical asymptotes. When is the denominator equal to 0? Okay, plus or minus 1. So we say x equals plus or minus 1. We don't just say plus or minus 1. They are vertical lines. So x equals plus or minus 1. Now, for the horizontal asymptotes again, all we need to look at is the terms with the largest degree. Because if I put 1,000,000 in for x, does subtracting 2 or subtracting 1 have much effect? Not really. So those are almost irrelevant when we're talking about really, really big numbers. So if I had x equals, or y equals x over x squared, that would reduce to 1 over x. Now, when I put really, really large values in there for x, what happens to the fraction 1 over x then? So if I put in 10 for x, 100, 1,000, 10,000, 100,000, million, 10 million. As I keep putting in bigger and bigger numbers for x, what happens to the value of 1 over x? Getting smaller and smaller. And it's getting closer and closer to what actual number? 0. Okay? So whenever the degree of the numerator is less than the degree of the denominator, our horizontal asymptote is going to be y equals 0. Because as the values of x get larger and larger, that fraction is getting smaller and smaller, so it's getting closer and closer to 0. All right, so graphing this then. We have a 0 at 2. Now, we also have a y-intercept, right? Anybody tell me what the y-intercept is here? What do we know about the y-intercept? The y-intercept is on the x-axis, right? Or the y-axis. What's the value of x on the y-intercept? The value of x for the y-intercept. So we're talking about a number on the y-axis. What's the value of x here? It's equal to 0, right? Okay. So if I put 0 in for x, then in the numerator I'm going to have negative 2, right? In the denominator I'm going to have negative 1. And negative 2 divided by negative 1 is, or positive 2. Okay? So we have y-intercept at positive 2. Okay? Now, our vertical asymptotes are at plus or minus 1. So I'm going to draw a vertical asymptote, a dotted line, through negative 1 and through positive 1. And then I have a horizontal asymptote at y equals 0. So on the x-axis, I have a dotted line to represent the horizontal asymptote. And this means that as x gets really, really large, it's going to be closer to the x-axis. As x gets really, really small, it's going to get closer and closer to the x-axis. All right. So let's talk about graphing it then. Okay. Now I know that Chris has graphed it already, and he's kind of wondering why it does what it does. Okay, and I'm going to tell you. Okay. Now, pick a number. So to the left of -1, either the graph is going to be in the second quadrant, or it's going to be in the third quadrant, depending on whether the y values are positive or they're negative. Okay? Because it's going to look like 1 over x. Okay? So now, how do I figure that out? Easy. We put a number in for x. Okay? Let's choose -3. If I put -3 in for x, we get -3 minus 2 over -3 squared minus 1. Okay? I just picked any number over here because I want to know whether it's in the positive side or the negative side. So we get -5 in the numerator, and what's -3 squared? Okay, positive 9, and 9 minus 1 is 8. Okay, so at -3 we have -5/8, which is about here. So this tells me that the graph on the left side of -1 is going to be in the negative values, which means the graph is going to look like this over here. It's going to look like our parent function, 1 over x. Now, so this is what happens then. Where's it going to the left side of this vertical asymptote? The graph is going down to -infinity here, right? So when I cross the vertical asymptote, it's going to go up to positive infinity. Okay? Now, so as this graph comes down, it has to hit that 0, correct, or the y-intercept. Now, can the graph keep going down? I can't cross the vertical asymptote. And if my graph keeps going down, it's got to go through the x-axis, doesn't it? Well, if it goes through the x-axis, that means there's a 0 there. Is there a 0 there? No, there's not. So it can't go through the x-axis. It's got to turn around and go back the other direction. Okay. Now, on the left-hand side of this other vertical asymptote, it goes to positive infinity, right? So when it goes across the vertical asymptote, it has to go down to -infinity. Okay. So it's coming up from -infinity, but there's a 0 here, right? So it's got to go through that 0, but since there's a horizontal asymptote here, it goes through the 0, comes back down, and goes along the asymptote. Is that what yours looks like, Chris? Okay. But think about it for a second, all right? That here's our parent function, it just happens to be right there. The graph of that parent function looks like this, doesn't it? Okay. So these two parts kind of look like that too, don't they? Very similar to it. The only difference over here on the right-hand side is because of the 0 meant it had to go through the x-axis, but then it's got to come back to it. Here's the thing. We can cross a horizontal asymptote, okay? Because horizontal asymptotes are for very, very large values of x and very, very small values of x. But we can't cross a vertical asymptote because those are for actual values of x, and it doesn't exist there. So this is what your graph would look like. Right? Did somebody graph it and not get that? David, did you? And let's see where your error is. Oh, you didn't put x minus 2 in the numerator. The reason is because you had x minus 1, so you actually had a hole in your graph. There you go. Okay? All right. So there's two of the scenarios with the horizontal asymptotes. Real quickly, I'm going to hit the third one for you. Let's look at letter C here. And I'm just going to talk about this. I'm not actually going to go through and do this problem, okay? All right. Here's the difference, okay? Here's our third scenario for horizontal asymptotes for the end behavior. Notice here, in the numerator, what's the leading coefficient term? It's 3x squared, right? Okay. So our largest term here is 3x squared. What's the largest one in the denominator? X squared. Okay. So as I deal with really, really large values of x, this plus x and this minus 9 don't really have any value. Okay. They so small, no effect. So look at this rational function we have. What happens when I simplify this? What do I get? Okay. The x squareds cancel. I'm left with 3, right? So this is going to have a horizontal asymptote at y equals 3. Okay. So we have three things that can happen horizontally. None, okay, if the degree of the numerator is larger. Y equals 0 if the degree of the denominator is larger. And if their degrees are the same, like in this case for letter C here, 3x squared over x squared, then all I have to do is simplify that fraction, and I get my horizontal asymptote. And all that stuff is on here. Okay, a little hard to read sometimes, but it's all here. Okay. Just need to take your time and work through it. All right, now there's one more situation that can happen that we're going to look at. All right, and that's if there's a hole in your graph. And Mr. Brandt over there, we're gonna talk about David for just a second. And I want you guys to do this. Don't put this in your calculator. All right. I want you. How many of you had? How many of you just had this in your calculator a moment ago? Okay. All right. I want you to go put this back in your calculator, but instead of putting a 2 there, put a 1 there. Now, wouldn't you think we'd have a very similar graph to the one we just had previously? Okay. Okay. So if I look at my graph, it looks like this. Okay. Now, the thing is that in this problem here, we had two vertical asymptotes, didn't we? How many of them do you see on our graph? There's only one there, right? There's a vertical asymptote at, looks like probably -1. X equals -1. Okay? But from that problem, we said that there was vertical asymptotes at +1 and -1, at +1 and -1. So, but there's not one at +1. Take your calculator and hit trace and put in +1. You get no answer. If I go to the table, At positive 1, it says there's an error there. Okay. All right, that's interesting. But if we change this to x minus 1 over x plus 1 times x minus 1, what do you see? They cancel out. You have a common factor in the numerator and the denominator. Okay. So according to this, we have a 0 in the numerator, don't we? But the denominator also equals 0 at the same spot. Okay. When that happens, we have what occurs as a hole in the graph. So take your calculator and change your window. Okay. Go to your window and go from 0 for your x min to 2 for your x max. So we're going to focus in on that, where that other asymptote was supposed to be, or that other 0 was supposed to be. Okay? And then graph it.
Whoa, that's weird. I don't understand.
Now, if you look at it up on the screen here, what do you see?
The hole.
There's a hole there. Okay? The function does not exist there. You can't have a 0 and a vertical asymptote at the same time. So what it does is it creates a hole. So if we were to put 1 in there, so here's where that hole is at specifically. So I could cross these out, right? And so in the numerator we have 1, in the denominator we have x plus 1. Okay? So if I put 1 in here for x, what do I get? 1/2. Okay? So if we trace now, and notice I'm at the point 1, and there's nothing here, right? So it's sitting on that hole right now. Look at the numbers then, that when I go to the right, it's very close to 0.5. When I go to the left, it's very close to 0.5. So where that hole exists, that hole is actually at the point 1, 1/2. Okay, the x value is 1, the y value is 1/2, is where that hole is. We can actually find out where it is exactly. Okay. So let's look at this problem. So if the numerator and the denominator have a common factor, then there's a hole in the graph at that x value. So here we have x squared minus 9 over x minus 3. I factor it. Get x plus 3, x minus 3 over x minus 3. According to this, there are zeros at 3 and negative 3, right? Because that's where the numerator is equal to 0. According to this, there's a vertical asymptote at x equals 3, because that's where the denominator is equal to 0. But the point is, I can't have a 0 and a vertical asymptote at the same spot. And so that means then that I have a hole at 3. And we're always talking about x values. Okay. So if I cancel these x minus 3's out, I get the function, or I get y equals x plus 3. Well, what's y equals x plus 3? What's the graph of that look like? X plus 3. Okay. That's just a line, isn't it? Okay. With a y-intercept of 3 and a slope of 1. Okay. So all this is the graph of a line that looks like this. Let's see. I don't want that. Undo. That's all that is. It's the graph of the line y equals x plus 3, but it has a hole at x equals 3. And if I put 3 in here for x, what do I get? 6. So my hole is exactly at the point 36. All we need to do is represent the x value, but when you graph it, you need to show exactly where that hole is, and that hole is at the point 36. And so if I graph that function, x squared minus 9 in the numerator, x, what was it, plus 3 in the denominator. If I graph, oops, is that minus 3 in the denominator? Oh yeah, yep. If I graph it, there's the line y equals x plus 3. If I hit trace at 3, it's undefined because there's a hole there. And so if I zoomed in on that point, if I went from 2 to 4 on the x, 5 to 7 on the y, my graph has a hole in it.